Hello everyone. Welcome to the first SciML external seminar of 2025. Today's speaker is Dr. Ben Booth from the UK Met Office, and has very kindly come all the way up to Leeds from Exeter, so very welcome. Ben.
Donald. So I'm Ben Booth. I've been at the Met Office for about 20 years, and I've been working in national climate scenario information for national climate adaptation, I guess. And I have a interest in uncertainty and how you kind of capture the wider uncertainties in future climate change and expose them to climate impact and adaptation. And I worked closely with colleagues here, like Ben Booth, on adaptation. But I had a change of career in late last year, and I saw an opportunity around AI downscaling and jumped at it. So I've shifted gear. I've got a new group looking at this. So I will introduce myself and a bit about the tools we're using. I also want to say a bit about why I think it's such a good opportunity and what the AI brings to that station that we couldn't do. So, can everyone hear me online, or can somebody hear me online?
Yes, you're very clear.
Great, thank you. So, about 800 research scientists at the Met Office. Not all of us work on numerical models, but most of us work on numerical models. So this is a graphical representation of movement of discretization of the globe, and we kind of use numerical models for weather prediction, climate research. But one of the kind of main motivations is to kind of keep a seamless approach. So by developing models that do well at weather forecasting timescales, you have greater confidence in your ability of your models to do processes appropriately at climate timescales. So slowly, I mean, we've been using these models since as long as I've been alive, and slowly they've been getting better through development and time. But there's a really interesting movement that's going on at the moment. So so earlier this week, the European Centre for Medium Range Forecasting has formally operationalized its AI version of its weather forecasting. AI is making really rapid progress in being able to reproduce skill, predictability, and timescales. And it's quite interesting to watch. It has been interesting to watch. So it's gone really from very little 4 years ago to being very competitive now. So this is a graphic showing RMS errors compared compared to the dynamical forest forecast. That's a high resolution IFS on the top, and the colors where they're blue are more skillful, and where they're red they're less skillful. And so the top three are numerical weather forecasts, and all the ones in red down here are different AI forecasts. And for these large scale variables, so geopotential high, temperature, humidity, and wind vectors, many of these models like GraphCast and Fuji are doing very well compared to the rest of the two numerical weather predictions. We kind of knew this a year or two ago, and the argument was, well, that's great, but these are large scale variables and not related to surface variables like precip, which are kind of drive impact. But late last year, we're starting to get models that now can do things like precipitation as good as or better than numerical weather forecasts. So that's GraphCast here. So this is really kind of causing a lot of existential conversations where I work about what role AI may have on climate timescales, and where we should be looking for AI rather than traditional numerical prediction to address problems. So it's a different situation in that for weather forecasting, the information needed to predict tomorrow based on today is all contained in the historical record. So it's a very well-defined data science challenge. Whereas it's not yet obvious to many of us, to most of us, what the similar well-defined data science challenge would be in the climate prediction context. So this is just a graphic on the right-hand side showing the trend in global temperature. And the projections are for a continual increase beyond the warming we've already seen. And so the kind of historical record does not provide the trained data set to kind of inform what that future world may look like. But where are the opportunities? So before I'm going to talk about the work of the group that I work with, we kind of to try and explore this. There's a couple of flagship projects at the Met Office. So one is a data-driven climate modelling flagship, which is led by Doug McNeil, and the other one is the AI Downscaling, which I lead. So the data-driven climate modelling is really an explorative approach to kind of look at the various ways we think AI can play a role in that climate context. So it's looking at foundation models, it's looking at the potential for using AI for emulation, it's looking at the potential for using AI to come up with large initial condition ensembles around seasonal forecasts. So they're currently exploring Aurora, which is one of the open foundation models that's available out there at the moment. And that group has a remit over the next year or two to kind of start mapping out opportunities and see that going. So the other activity, which is mine, is kind of AI downscaling. And I like this because I can really see a data-driven challenge in AI downscaling. So those of you who are not familiar with, so I assume that most of you are not familiar with downscaling. So we have a lot of, all our information on global climate change comes from these numerical models of the climate system, which enable us to explore what different future emission scenarios may mean for global climate. And so we have a comparatively rich amount of information at the global scale, but the resolution of those models is very coarse. So I'm going to walk away from the mic. I'll be back. So just to kind of visualize that, on the top is temperature and rainfall from a global model for over Europe. And you can see, my wife is Italian, and you can see that Italy does not exist. So you cannot say anything about Italy from a global perspective. You can also tell that Brexit hasn't happened. The UK is still connected to Europe. So there are you're not able to resolve that kind of local scale information, whereas the regional models are able to resolve orography much better, land sea contrasts. You can see Italy on there, and there's also lots of structure. If you look at the rainfall, orography and coastal structure really dominates where you experience a rainfall in that domain, and that's really not captured in the global modeling simulations. And so what we traditionally do in terms of translating global climate projection to that local scale is to run dynamical regional simulations. So just taking a subdomain, doing a lot of resolution, taking boundary conditions from the global models and translating what that global climate projection means at local scales. And that I think is a really nicely data-defined AI problem, in that if you have enough regional simulations that tell us the relationship between the global models and the regional detail, we can hope that the AI can pick up that relationship and potentially translate any global simulation down to that local scale. So that's the kind of the ambition. So why are regional models important? As I said, there's lots of work that's done on most of our information about global climate change at the global scale. But when you come down to impact, or impacts are local, so this is a figure from UK CP18, so the latest UK national climate scenario data, and we provide global projections, which is actually much higher resolution than the ones I showed before, but also regional simulations at 12 kilometers and 2.2 kilometers. You can see the difference of what those models can resolve. And so if you're looking at flooding on river catchments, you really need to kind of start resolving whether the rainfall is falling on the east or the west of the Pennines. And you need to go down to that kind of scale to kind of catch that process. This is a very old slide that I borrowed from Suraj, and it's a bit noisy. Basically, on this slide, there's each row is dated 10 years old, but it makes the point really well. Each row on this table is a national climate scenario data produced by different countries across Europe. And looking at the time horizons and number ensembles from global models, which is TCMs, and regional models, which is RCMs, and other properties. But the important point to make here, there are seats over this side. The point to make here is that the regional models are a really key part of all climate national scenarios across Europe. And so our ability to kind of translate global projections to that scale is, and they are important because you want physically consistent information between different variables at high resolution. It's probably the only tool we currently have that can provide that. So they play a really important role in national climate adaptation plans. So that's a bit about the background. So we've been exploring AI downscaling and training on these regional simulations to explore to what extent we can supplement existing simulations. So we're collaborating with Henry Edison and Peter Watson and Bristol University, who've developed a diffusion-based downscaling model. And I believe, and Antoine Duret and Samuel Saumont in CNRM in France. I think Antoine came and gave a seminar here before Christmas.
Yeah, he did.
So if you were there for that seminar, you're aware of one of the models we're using in-house. And we're collaborating very closely with Leeds University in Joburg, applying downscaling models in a southern African context. So a bit about the kind of the choice of algorithms that we're using. So they're all from computer vision tool sets, and essentially there are 4 particular approaches that are being used by current groups around the world. We're adopting a UNet that Antoine Duret has developed, and a diffusion model that Henry Edison's developed. There are some very credible applications using GANs, so Neelish Rampal and Niwa in New Zealand.
Hello, looks like you're muted. We can't hear online.
Myself. So can you hear me now?
Yeah, we can hear. Thanks.
Fantastic. I'm not sure how I got muted, but thank you for pointing it out. This is a diffusion model. It's a slide trying to. So a diffusion model. So there's a series of pictures of dogs in the central panel, and what you're doing in a diffusion model is you're learning how to denoise, how to noise an image. So when you move from that dog to a pure noise in your pixels, you're actually having to add structure. You're having to add particular structure to take out the eyes and to take out the nose, and the features around the eyes and the nose are lighter, but not around the ears. And so that you're learning how to take out information, in this case a dog, from a picture. And by learning that noising step, you can reverse it and denoise it. And you can then ask, can you produce a picture of a dog or an astronaut, or can you produce a photograph of an astronaut riding a horse? So that they kind of I'll come on to some of the useful points about it in a tick, just to kind of give another way of representing this. So this is a stable diffusion example. So what I've done here is I've trained stable diffusion on me, so that's Ben on the left hand side. So I've asked it to learn the features of Ben, and then stable diffusion has already been trained to know the features of the Queen of England in oil, or 1950s superheroes. So you can then ask stable diffusion, can you produce a picture of me as the Queen of England? And this and it has what a really nice feature of diffusion models is it can do its generative properties. It can come up with multiple realizations given that large scale driver. So it can come up with multiple images of me as a biker. So this kind of demonstrates that I'm a narcissist, but it also kind of actually illustrates the kind of what the diffusion model is doing. So these are 2D images, and we're doing exactly the same essentially in a climate context. So we're taking what we're doing in the downscaling is we're taking large scale variables, in this case specific humidity at different temperature and vorticity at different heights in the atmosphere, surface pressure. And we're asking it to learn the relationship between those large scale synoptic variables and surface rainfall at high resolution. And once you train that successfully, you can then say, ask it what is the rainfall for a particular sets of large scale synoptic drivers. And it can also come up with multiple realizations of what that local weather looks like given those large scale synoptic drivers. So that's the diffusion model. I just got one slide on the UNet. This is a slide that you may have seen if you've been to Antoine's seminar before Christmas. So the UNet is a simpler. It's like a CNN, but it retains it's better at retaining small scale features. And what he's doing here is he's emulating his regional model with his UNet model, and you can capture much of the kind of the variability in temperature in this case due to orography. So a global model would not separate Toulouse and the Pyrenees. It'd be all in one grid box, which is largely low level. And what he's showing here in the time series is that the emulator can capture the RCM at the Pyrenees and in Toulouse, whereas the core scale information wouldn't be able to resolve this orography and would suggest it'd be much warmer in the Pyrenees point. It's not just a mean difference it's picking up, which is reflected in the maps. There's also a difference in variability. So if you look closely at the green and red, there's more variability at high altitude than there is at low altitude. And the emulator is able to pick up that increased variability. So there's some really nice properties that come out of these downscaling algorithms. So we've got two models. We want to work with both of them because we think they both bring different properties to play that are useful. So starting with the diffusion model, what's really exciting is that it generates samples of local weather given large scale drivers, so multiple realizations, and it has some really nice applications, say for event attribution and other challenges. And it avoids smoothing out heterogeneous fields. So rainfall is very heterogeneous, and sort of a CNN or UNet will tend to smooth it out in its prediction, whereas the diffusion model really kind of really capture that kind of high intensity rainfall events occur in very small number of pixels. But the limitations are it probably requires much larger training volumes to effectively train the diffusive part. So there's not to effectively train the generative samples. So the generative samples, we're really interested to what extent generative samples are informed by the training data. And the other limitation is that at sub-daily timescales, because it's stochastic, you can lose temporal coherence, and so we need to try to work out how to get around that aspect. And then the unit models are much more efficient to train, so we can probably do something useful with smaller training volumes. They're deterministic, so they're inherently they get temporal coherence at sub-daily timescales because they are deterministic. So there are pros and cons, and we want to employ both, and they'll probably be useful in different applications. So that's mainly what I'm going to say about the methods and where we're going. So we've got some early progress. We've got a perspective piece that's currently onto review in BAMS, and at the bottom are some early work looking at the diffusion model. So on the left-hand side is the actual regional convective emitting regional simulation, and the next 5 is our diffusion model trained on complete outer sample data, and I'm quite pleased by how well it looks like it's doing. So it's capturing the spatial structures quite well. So that's what I'm going to say about the methods, and we can come back and have a chat about that at the end. I want to say a bit about the motivation, about why I think AI downscaling is important, and where I think it can play a real role in kind of filling some of the information gap we have in adaptation. So I've got a couple of aspects I want to bring out about. So first one about about regional hazards. I'll come back to this figure in a tick. So I want you to imagine that you have responsibility for ensuring that Switzerland has infrastructure that means it's resilient to future water shortages. So Switzerland is an alpine country. It has valleys that a couple of kilometers will change whether the rain will flow north or south. And you know that the future projections are for summer drying, so there's less rainfall in the summer. You kind of want to know whether the winters are going to bring and will enable you to recharge your reservoirs and enable you to have water in the summer. You may well be aware that there are new kilometre scale regional simulations over the Alpine domain. In fact, it's the world's richest current data set of kilometre scale regional simulations anywhere in the world. We have 7 different models who produced kilometre scale climate projections for a common scenario. So that might be very attractive because they can actually resolve start to resolve your alpine valleys. So let's have a look at that winter climate change in the climate projections. So here we are. This is a bit of a busy plot, but I want you to stay with me if you can. There are red dots on here. What I'm showing you is the climate change to mid-century. So it's wetter on the top half of this plot and dry on the bottom half, and it's warmer as you go to the right. And there's 7 red crosses here, and they are the projections for winter mean seasonal rainfall change to mid-century. And they all show a common neutral to wet, a modest to low end warming, and they show that climate change response because the global climate models, which the green circles that they are downscaling, all happen to produce projections that were moist and modest warming. But from a hazard point of view, this is a challenge. So the underlying contours is what we think the wider range of future climate changes are likely to be in the Alpine domain. So if you were to, in fact, experience warmer conditions than those simulations suggest, then there'll be less snowpack, less spring river flow, and greater water demand. If you had drier conditions, you would limit your ability to recharge reservoirs in the winter. So there are important parts of the climate hazard that aren't captured by those kilometre scale simulations. And this is where I think AI downscaling can really come into its own, in that if we can learn transferable relationships between the available simulations down to kilometre scale, can we then go to a much wider range of global projections, which I'm showing on the bottom left, so all the yellow dots down there, and downscale any one of those down to that kilometre scale. So you can identify simulations in the wider global projections that are much warmer or much drier. And so AI downscaling can enable you to kind of capture that wider climate hazard. I really like the one on the right. So just to explain what that is, this is a range of climate projections to mid-century from a single large initial conditional sample. So for those of you not come across these, they're just exploring the difference in those green dots. It's just what you expect from natural variability alone. So it doesn't explore all the range of warming, but all the range of decadal scale rainfall change, whether it's going to get much wetter, much drier, is basically explained by natural variability. And that's something that nobody in the provisional climate adaptation information has ever really managed to expose. So AI downscaling may mean we can start looking at the role of variability in climate change at the hazard scale first time. So I think this is really exciting in terms of what it can bring to the table. So there's the second area, the second motivation I want to put in front of you is thinking about how we can use downscaling well-controlled regional simulations to get better estimates of regional climate change. And so before I come on to that point, this is a table from Martin Wild's 2012 paper looking at observed surface solar radiation. So this is basically global dimming or global brightening. So air pollution increases up until the 80s, led to less sunlight getting to the surface. That was what we call global dimming. So that's the kind of the decrease in solar radiation in the 50s to the 80s. And since then, some regions of the world have experienced local brightening, where air pollution mitigation has led to more sunlight coming to the surface. So especially true of Europe and North America, or a region like India, where we're still experiencing dimming out twice a day. So this is not global greenhouse gas driven global climate change, but regionally can have important climate. It can be an important climate driver. So I just wanted you to keep that context in mind. I've got 3 on this. So if you look at European climate projections out to mid-century, there is a difference between the regional simulations, which is the top row, and the global simulations, which is the middle row. So the global simulations tend to be warmer and drier than the regional simulations. So this has been something that's puzzled us. In the last couple of years, I think we now understand it, but it puzzled us for a while. And you can see the difference in the bottom. So there is a difference between in the climate change projections you get from regional simulations and global simulations. So why is so that's showing that same information in a different way. So the orange dots here are warming to mid-century over Europe, and it's this box down here. And the green dots are the warming over that Central European region from the regional simulations. You can see that they are on average cooler than the global simulations. And then I've picked out here in the 7 triangles, the global simulations, which are used to drive those 53 regional simulations down here. And you can see there's systematically cooler. And at the lower end, the lowest regional simulations capture only half the warming of the global climate model. It's downscaling. If you remember at the beginning of this talk, these regional simulations are what we are using to inform adaptation across Europe, with the exception of the UK. So potentially we're adapting to a more optimistic picture about climate change over Europe than is really there. So why is that? So this is going back to that dimming brightening context I introduced. So if you look at the global, so what I'm showing you here is global on the left and regional on the right. I'm showing you change in surface shortwave trend between now and mid-century. Global runs, regional runs, and there's a spread in both. But what you can hopefully see is the regional runs tend to have a much less negative trend So this is the European brightening that we see in observations and global models, and many of the regional models neglect that regional brightening at all. And we can understand why they neglect it, because they don't actually account for that change in aerosols, which drives that change. So there's a systematic difference between what the global models are representing and what the regional models are representing. And well, I'm showing you the same thing here, but instead of temperature, instead of shortwave radiation, I'm showing this for temperature. And you can see the regional simulations tend to be cooler on average than global simulations in that trend. And if you look at, I can do correlation plots if I had more time, but by eye, hopefully you can see that the pale blue one up here, there's a strong correlation between the difference in shortwave trends, the lack or otherwise of brightening trend, and temperature response. So we can, there are structural differences between the available regional simulations and the global simulations, which we can understand and which have consequences on what those regional simulations mean for climate projections. And I can show this for different world regions, so China, Europe, North America, Mexico. But the point is that we can understand why regional models may over or underestimate global models because of whether they represent aerosols in this case or not. But I think this is important. I think this is interesting because you can go away and do the same experiments. So these are new global and regional experiments we've done in-house. Simon Tucker led, where we spent a lot of time developing regional simulations which match the aerosol response of the parent global climate model. So the parent global climate model, and these are the regional simulations that they drove. And you can see much more consistent temperature responses between the regional and the global models. So where does AI downscaling come into this? So I think this is in. I think. So I think AI downscaling. I think we have an opportunity where we can really think about training data sets and constructing training data sets which have consistent processes from global and regional, and then training your AI relationships on these simulations, and then that potentially enables you to correct the entire ensemble and provide regional level information which doesn't have this kind of systematic biases with data sets. So it's kind of an opportunity to kind of tie up the AI downscaling with the modeling capability in a consistent way, and by thinking a bit more about it, come up with better training sets that correct some of the biases that we kind of know are there already. So those are my two kind of motivations. That's why I kind of think AI downscaling is particularly important and what caused me to jump ship in May last year. So I think I've got maybe 4 or 5 slides just about where we're going to go from here. So just to kind of summarize that, so I think regional simulations are really important for climate adaptation, and particularly in Europe, where they're probably the prime source of information. But there are limitations in terms of number of global simulations they can project and downscale. But there are also structural limitations in what's out there currently. And I think AI downscaling has potential to kind of address both those issues, the kind of lack of coverage and some of the structural features. So who are we? Where are we going? So we're a new team. So I've been in post since May last year. There's Robin Clark, Tom Everall, Kate Halliday, and John Caesar, and we're the core team. And so we're working on the unit model and the diffusion model to evaluate and further develop where needed. And then we were engaging with other people at the Met Office currently who are potentially interested in using downscaling. So we're talking with Lewis Blunt at Urban Scale Modeling. We're talking with Simon Tucker about applying this in the African domain. We're working with Grace Redmond and Hamish Steptoe, thinking about East Asia. We're talking with Dan Cotterill and Georgie Logan about event attribution, and I come on to that in a tick. But and then there are applications in marine seasonal and mitigation. So the main applications we see is kind of supplementing existing regional or kilometre scale simulations, and that's the kind of motivation I've kind of outlined in the last part of the talk, and event attribution. So the diffusion models in particular can produce these samples of local rainfall given common synoptic drivers. And I think that probably makes it really attractive to kind of look at event attribution. So if we can train this well, we can come up with large ensembles quite rapidly of particular extreme events with and without climate change in a much faster timescale than it takes us to kind of run regional simulations. So we have these issues where we'd have a very large storm or flooding or a wind event in Northern Ireland, as it happened earlier this year, and then it takes us about 9 months to run the simulations with a statement about whether that 20% due to climate change or not. And by that time, the world has moved on. And so I think the AI downscaling can shortcut some of that. We're also looking at sort of storm surge modeling. So we have really nice data sets in the Met Office looking at storm surges. And again, it's a very similar data-rich situation where we've got relationships between large-scale global collections, storm surges that can be planned. So those are the kind of application areas. So we're currently in a learning phase, so we're learning about the AI tools. We're trying to get ourselves up to speed. We're trying to understand what they do and why they do what they do. But we're also trying to understand those different applications and what those different applications we want to see AI being able to do before they would feel comfortable or confident to put it in front of decision makers. That's a kind of really important process that we're kind of engaging. That's our emphasis, I guess, in the next 3 to 6 months, is to better understand that landscape. And that's going to inform benchmarks. So the focus of the group is to kind of use that understanding of what the user needs are for the different applications to come up with benchmarks, which tells us how well the different models are doing. And I'll say a bit about benchmarks. So I think benchmarks are really key to how you kind of develop and use and eventually roll out AI. So we're new to this, we're spinning up, but we see that process of kind of understanding the application needs and thinking about how to kind of test and evaluate that in a benchmark. So initially, that's going to help tell us which one of our AI models is best in particular applications. You can by developing a benchmark and developing validation metrics that tells you how well it's doing against those properties. And I come back to what those benchmarks may be in a tick. Then we can evaluate which of those models are best. Once you have those benchmarks set up, then they provide a really good framework for iterative development. So you can, if you're looking at outer sample extremes, and you can demonstrate that your particular downscaling algorithm is failing to capture the magnitude of outer sample extremes, you might have various things you want to do to improve, and having a benchmark means you can rapidly test and evaluate ideas. But if you do this well, having a transparent and visible benchmark is a way that we can demonstrate to users, look, these algorithms can do well at these particular applications in these needs, but you might not want to use them in these other contexts. It's a transparent way of demonstrating skill, and particularly from the Met Office, we have a long history of providing climate science information to find decisions, and there's a lot of interest in using AI, but we need to be able to demonstrate that AI brings skill, and you can have where you can and cannot have confidence in using that. So that's will be a big part of the kind of focus of my group over the next year or so. So just to kind of pick up on those kind of benchmarks and user needs. So the different applications of AI have different implications for what we need the downscaling algorithms to do. So I've kind of mentioned event attribution, I've mentioned supplementing existing regional simulations. So if we want to use AI to supplement regional simulations, we want to make sure that it does well at daily, subdaily sample extremes. We want to make sure it can capture multivariate coherence between rainfall and winds or other variables. We want to really test its transferability. So can you learn the relationships between one global model and one high resolution regional model and confidently predict how to sample regional model driven model? So that transferability is really key if you want to be able to use it in that context. And we want to make sure, particularly for things like drought, that it has a temporal coherence or subdaily rainfall. If you look at the event attribution, you don't need that transferability. And many of the attribution statements actually are a single variate. So there may be, there's a different set of application needs that you need to test. So the subdaily extremes are really important. The temporal coherence is really important. So what we're trying to do now is better understand those application needs and then capture those in our benchmark. So I think this is kind of what I wanted to outline. So I've kind of introduced us. We're a new team. I've tried to motivate why I'm excited about AI downscaling, why I think it plays a role. And I've introduced the different algorithms and approaches that we're using. And I'm really happy to have conversations on any or all of those.
Okay, do we have questions for Ben?
And thanks, that's really really great. Thank you. I had a question about boundary conditions actually. So in the RCM case, the RCM, if it's showing consistently different rainfall, I'd worry about the boundary conditions being incompatible. The horizontal moisture fluxes being incompatible with the driving model. I mean, that's one question for RCMs, but then for an AI-based model, do you have to kind of put a constraint on these sort of bulk, or do you benefit from putting a constraint on, say, bulk or energy terms in the same way? Thinking about this sort of aerosol radiation.
So you're thinking about the inconsistency I showed between the regional and global ones in terms of trends,
or in terms of those analyses you showed with the RCM being consistently better and cooler.
Yeah.
So I would wonder, just as an RCM question, that means that the boundary conditions are being kind of sort of violated. But then an AI model, you've got the same issue. How do you maintain consistency with the sort of bulk conserved quantities like energy and water, which you should conserve?
You're thinking about this case here. So
I was thinking about the European biases. These ones.
Yeah. So the AI downscaling can only be as good as the training data, and so if you were to naively train a downscaling relationship between these global models, these regional simulations, you'd be training in the biases in that process. Absolutely. So this is AI is biases in. We have to be really careful about biases in the training data and what they mean. So I like AI downscaling because it's a nicely defined data-driven challenge in that how do you emulate what the added value is of a regional simulation, but it's only going to be as good as that regional simulation. So we're not proposing in our group to think about bias correcting that at this stage. So what I think we want to do is we want to demonstrate skill in that emulation stage. And once we have skill in that emulation stage, then we think we're in a much better position to kind of think about how do we bias correct with respect to energy conservation or local observations. And
you talked a lot about the link between the global model and the regional model. What about the observations at the regional scale? You didn't really say how they're folded into this learning.
So there are that question is the most common question we get asked, and I think it's a really important one. And there is a real split in the regional in the downscaling community, in that half the downscaling community is doing this a bit in observational space. So they're looking at error and high resolution regional reanalysis, And so Theo Kvasgaard in Denmark, for example, is doing this with the same tools that we are in observational space. And then the other half of the community is doing this as an emulation challenge. I mean, can you emulate the added value of the regional model? And we're going to have to join those up at some stage. I'm suggesting that my team wouldn't do would focus on the emulation stage in the first couple of years at least, because we're currently comfortable putting regional simulations in front of users, say UK CP 18. So if we can demonstrate we can provide comparable skill, then we have something we can already put in front of users. But I agree. I think once you can do that, bringing in observations is a really important part of.
Presumably the observations are often too sparse to use as a training data set compared to the huge amount of data you have in the regional model at any time resolution you want.
Yeah.
Much less data, isn't there, to learn from?
There's huge heterogeneity. So the UK has no regional reanalysis for the UK. It doesn't exist. But other European countries have invested in that, and so they have high resolution regional reanalysis data sets, which do lend themselves to that kind of that training. And so there's a real conversation going on internally in the Met Office about to what extent we need to step back and think about regional reanalysis as a tool.
I guess you pointed out at the beginning that resolving the orography and the coastlines is crucial in scaling. So presumably those things are fed in as input. How much does it learn from that? And then does that mean that you can transfer it? So you can train a model on one domain and then apply it to a different domain? Do you have any comments on that one?
So in the results I've shown, we have not used orography or land contrast in training at all. And it does really well, but it's learning. It must be learning about the impact of orography, because that grid point or that pixel will be impacted by the fact that the Welsh Mountains are to the west. Lewis Blunn is very interested in that transferability question. So he has 300 meter simulations over London and Paris, but only 3 months each. And so you gain a lot of information about convective rainfall, especially at that high resolution. He wants to know, can you use AI spatially translate that information? And I think that's a much harder challenge. Erica Coppola in ICTP is doing something very similar. So I think there is an active area in AI Downscaled thinking about how transferable are those relationships. And you're right, you have to bring in things like orography, bring information about whether there is a mountain between coastline and a grid point, or for a particular wind direction. I don't know how we do it. It's a harder challenge, but Lewis is interested in that and is working.
But the other transferability question is the one between models. So
yeah,
if you train on, say, low resolution UM going to high resolution UM, apply that to low resolution bench model.
Yeah.
How far have you got with that? Because it seems to me that the relationship, say, between coarse and high resolution rainfall depends on the parameterizations in your coarse model.
Yeah.
If you have a bad convective parameterization produced by rain, say, it sort of shouldn't be transferable in a thought experiment, but cheating always surprises me. So
yeah, I'm conscious that online you probably don't hear these questions. Shall I repeat that for you? So John's asked about transferability between different GCMs. So where the GCMs have different convection scales, convective parameterizations, can an RCM learn the relationship between one GCM and an RCM, different GCM with a different parameterization? That's it. So this is really live as a question, and the community is doing two things. So it's called perfect model training and imperfect model training, which I hate. I think those words don't describe what's going on. But perfect model training is saying, can you take a high resolution simulation and degrade it to core scale GCM scales and learn that relationship? So you're learning the added value of resolution, if you like, and you can see on a kilometer scale global model you can do that. And And then you apply that to the coarse scale fields from a different GCM to predict the answer. So that's easier to do. And most of the community is currently at that stage. Then there's the imperfect model training, where you do that same step, but you also learn the difference in the large scale flow or resolution regional model and the driving GCM. And if it, so if you think about going to compactor scale regional modeling from global modeling, that could be how resolving the orography or resolving convection changes the large scale flow and changes the large scale dynamics as a result. So that's what the imperfect model also brings in, and that's hard. So you can fudge it over the UK, because UK regional simulations are very near SSTs, which are prescribed from the global models, and the tropics are thin fields, the natural boundary conditions control a lot of the response. If you look at Africa, if you do that over Africa, it doesn't work. This is where we're hitting trouble, so what you can do very successfully over Africa in RCPMs is you can predict for any CP for Africa. So this is a high resolution kilometer scale simulations over Africa. What the high resolution information is based on coarse and scale regional information. I want to write on the board. Can I write on the board?
There's a pen over there, maybe.
Maybe. So I'm happy to have a chat afterwards. But you can do the perfect model training. So you can train on coarse and scale CPM over Africa, say driven by the MPI, and you can predict the high resolution CPM from its coarse and scale CPM driven by ISM. That works really well, but you can't predict the change in the large scale between the two because you have enough information. And so vector scale, so I think that's a big challenge, and I could give a seminar about what that is, because I think there's I think it's that's the frontier. I mean, that's one of the frontiers, and that has all kinds of implications tied up in there. So what that imperfect model training brings in is added value of resolving high resolution, which we want to capture. But it also brings in structural inconsistencies between global models and regional models in, say, different parameter translations, lack or otherwise of aerosol representation. And so you're asking the AI in the imperfect model training to learn the impact of all those things, some of which you want and some of which you don't want. And so I think as a downscaling community, we need to figure out how to navigate perfect model training or imperfect model training. I'm really happy to come back and give a whole seminar on that if you work well.
Yes, thanks for the great talk. And I have actually two questions, if that's okay. So the first one is that, so in the first part of your presentation, you talked about the computer vision pipelines, yeah, for your task.
Yeah.
And the stable diffusion as well as the they are both black box like computer vision models.
Yeah.
And so my question is that does explainability matter here? And if so, have you looked at that? And my second question is that you also talked about foundation models and large scale pre-trained models. You mentioned Aurora, if I got it right. And how did that perform compared to computer vision in supervised pipelines like this?
So how important is it? The first question is how important is explainability in employing these tools? And that's really, I mean, there's lots of conversations in the Met Office, and there are people who are proponents of both. So some say you should never be doing AI, applying AI tools without thinking about the explainability. There are others who are more. I think I want to demonstrate. I think we've got 2 years to demonstrate that the AI tools can be good emulators for the downscaling. And I'm going to push as hard as I can on that, demonstrate it. And once we have a tool which we can demonstrate sample data and skill, I'm really happy to sit back and say, okay, can we understand that skill? And so I've got a little bit of, there's only a few of us, most of us aren't coming from an AI background. So I think I'm going to approach it that way. But if there is interest in kind of bringing this explainability insight into the tools we're using, we're really happy to work. Great. The other one is have we used foundational models to look at the downscaling? And we haven't done that. There are others who are applying the foundational models in downscaling, but it's not something we look at. But again, this is a really new area for us, and we're really happy to collaborate. And if there are ideas here or elsewhere.
Yeah, thanks for the talk. So I guess this question is fairly related to the last one. With your diffusion models, you're generating lots of samples. In the slide that you showed, there's quite a variability between samples that you get. I think you said they're consistent with global drivers. So 2 questions. Are you concerned about the variability? Is that, I mean, it is a feature of diffusion that gets a lot of variability out, but then how can they all be consistent with the global drivers?
So we're really interested in that question. So the question for those online is there's in those samples, and that these are 4 samples of particular rain event given a large scale synoptic drivers, there's variability across them. Can we understand be comfortable with that range of variability? That's why, isn't it? That was the question. So the so I think we need to be able to answer that question before we could use it in, say, event attribution. And so we're looking at, so in principle, that kind of synoptic driver that's responsible for frontal rain system going through the UK has occurred many times in a large train data set. So we have 12 ensemble members, each of 140 years, going from 1950 to 2100, which we can use to train a diffusion model. And then we can look at how those rainfall events, the spread of rainfall events or synoptic condition, maybe on synoptic drivers, pairs across that training data set and what the diffusion produces. Then we can play games by reducing that training data set. So as you get to smaller and smaller levels, where do you start to see fall off in skill or the diffusion model stand? So if the diffusion model has been trained, it's only seen a synoptic set of synoptic drivers, something like it once, it's not going to be able to meaningfully inform the samples, but it will still generate the samples. That's the kind of challenge you have in current. So we want to come up with benchmarks that means that we can test that and then play with training volume size and just get a sense of what is the minimum volume size you need before you can have confidence that that into sample represents genuine local rainfall given from the synoptic drivers.
So when you calculate your uncertainty across the ensemble, say, the variability between the samples correspond or correlate with.
Yeah, could we do that as? Can you do that as ensemble as a whole? Would you want a precondition on synoptic? So this we're really early days, and if there are good ideas, I'm really happy to to collaborate and that. So that's if you've got good ideas about how we could quantify this.
Early days for me as well.